Hi, my name is D. Lilasha Kumar. My roll number is 24BQ180423. Today's seminar about counters. A comprehensive counters overview of counter types, operations, applications. Classification of counters, types of counters, up counter, down counter, up and down counter. Classification and IC implementations. Asynchronous and synchronous counters, special counters, Decade, Ring, Johnson, advantages, limitations, and conclusion. What are digital counters? A digital counter is a fundamental sequence logic circuit designed to store and count the number of times or specific event or process occurs, typically in response to a clock signal. Core properties: timing synchronized with clock signals, sequencing state transactions in a specific order, counting representing counters in binary or ABCD formats. Classification of counters. Digital counters are categorized by on how their internal flip-flops are clocked, which is significantly impacts their performance characteristics. Asynchronous counters. Synchronous counters, ripple counters, sequential clocking, only the flip-flops receives the external clock pulse. Ripple effect, change of state propagates through the counters. Slower speed, cumulative propagation, delay limits maximum frequency. Synchronous counters means parallel counters. Stimulates clocking, all flip-flops share a common clock signal. Higher speed, parallel clocking eliminates cumulative propagation delay. Complexity, requires additional combination logic for control. Asynchronous ripple counter. Definition: an asynchronous counter, also known as a ripple counter, is characterized by a sequential clocking mechanism where flip-flops are not triggered simultaneously. Key characteristics: sequential clocking, only the first flip-flop receives the external clock pulse. Ripple effect, changing of state propagates through the counter on flip-flop at a time. Simplicity, generally similar to design and construct due to straightforward cascade arrangement. Slower speed, cumulative propagation delay limits maximum operating frequency. Ripple counter operation and limitations. Operations, first of all. Sequential clocking means only flip-flop receives external clock pulse. Output of each flip-flop serves as clock input for next in chain. Ripple effect, state changes propagate through counter one by one. Limitations, cumulative propagation delay accumulates through chain. Momentarily unstable output as clock ripples through flip-flops. Timing glitches limit maximum operating frequency. Synchronous counter. Synchronous counters working principle. In a synchronous counter, all flip-flops are connected to a common clock signal, ensuring that their state changes occur simultaneously. All flip-flops change state at the same time, uses combinational logic to control toggle inputs. Circuit implementation. For a 4-bit synchronous up counter using JK flip-flops, Q0 always toggles with each clock pulse Q1. Toggle only when Q0 is high. Q2 toggles when both Q0 and Q1 are high. Synchronous counter advantages: higher speed operation. Parallel clocking eliminates cumulative propagation delay, allowing propagation at much higher frequency. Eliminated cumulative delay. No ripple effect means all state changes occur simultaneously, ensuring stable output. More reliability operation. Concurrent state changes provides predictable and reliable performance in high speed digital systems. Types of counters: up counter, down counter, up and down counter. Three types. Up counter increments stored value by 1, with each clock pulse counting in ascending sequence. Down counter decrements stored value by 1 with each clock pulse counting in descending sequence. Up and down counter combines functionalities of both up and down counters with a control input to determine counting direction. Special counters, decade counters. Definition: a decade counter, also known as a mode 10 counter or ABCD counter, is designed to count through 10 distant states 0 to 9 and then reset to 0. Key features: counts digital decimal digits 0 to 9, reset to 0 after reaching 9, provides binary representation for each decimal digit BCD. Applications to digital clocks, display systems, frequency meters, digital systems. Special counters, Ring and Johnson. Ring counter, a specialized sequential circuit formed by connecting the output of the last flip-flop in a straight register back to the input to the first flip-flop, creating a circular arrangement. Characteristics: typically initialized with a single 1 bit circulating through the flip-flop, while all other flip-flops hold the opposite state. An N flip-flop ring counter has unique states mod N counter. Applications: sequencing counter system on hot codes. Johnson counter. Definition: a modification of the ring counter where the inverted output of last flip-flop to the input of the first flip-flop. Characteristics: produce 2n unique states for an N flip-flop counter mod 2n counter. Similar to gray code sequence where only one bit changes at a time. Generates specific waveforms useful in timing circuits. Application of counters. Standard applications: digital clocks means count seconds, minutes and hours to display time. Frequency counters measure signal frequency by counting pulse over time. Timers generate precise time delay for event control. Event counters count produce products on assembly lines events. Memory addressing step through memory locating sequentially. State machines control flow in embedded systems. Technical and emerging applications: data acquisitions, frequency divers, ADCs, IoT devices, automation, defense systems. Counter ICs, common counters ICs. Selection criteria: count range, clock frequency, power consumption, output format. Count range modules determine the maximum count value required. An n-bit counter has maximum modules of 2 power n. Clock frequency ensures the IC can operate reliability at the required input clock frequency. Synchronous counters support higher frequency. Power consumption: consider the power budget, especially for battery powered designs. Some ICs are designed for ultra low current consumption. Output format decide where the output need to be in binary. Advantages and limitations: asynchronous counters, synchronous counters. Advantages: simple design with straightforward cascade arrangement. Lower component counter resulting in lower cost. Limitations: propagation delay affects maximum operating frequency. Sequential triggering introduced timing issues at high speeds. Synchronous counters. Advantages: faster operating with synchronous counter changes, no cumulative propagation delay or ripple effect. Limitations in synchronous counters: more complex design requiring additional logic gates. Higher cost due to increased component count. Summary and conclusion. Key takeaways: counters are fundamental sequential logic circuits using flip-flops to store and count events in response to clock signals. Asynchronous counters offer simplifying but suffer from propagating Delay. Synchronous counters provide faster, more reliable operation. Various counters types: up counter, down counter, up and down counter, special counters serves specific applications in digital systems. Counters find essential applications in digital clocks, frequency measurements, industrial automation, and advanced control systems. Counter types: up and down, decade, ring, Johnson. Applications: digital clocks, frequency counters, timers, event counters. Counters are fundamental building blocks in digital electronics, essential for conducting events, timing operations, and generating sequential in modern technology. Thanking you.